Hello, today I'm going to talk about what me and my team learned when we are designing elements for a steel shed. So here is the dimension of the steel shed assigned to our group, and the span of the shed is 7 meters, and its width is 12 meters, and the height is 8 meters. Note that there is no dimension on the left column in section AA. The roof pitch is 5 degrees. So we were not given the dimension of the left column, so we have to calculate it ourselves. We use the trigonometry method here, that cosine theta equals to the adjacent over the hypotenuse. Since we have the adjacent, we can calculate for hypotenuse. Then we use the Pythagoras theorem to obtain the height of the elevated roof pitch. So the elevated part is 0.65 meters, so that means the height of the left column is 7.35 meters. The first step to designing a steel shed is to calculate the dead load G, live load Q, and wind load. So what I have here now is the formula for the dead load G. For beams, we need to add together all the elements of permanent dead loads, which include load of roof sheathing, ceiling, insulation, services, purlins, and the self-weight of the beam. Next, we calculate the live load Q. So the formula is Q equals to 1.8 divided by A plus 0.12. So A is the area. So we got 0.16, but the minimum is 0.25. So we consider it as 0.25. To get the Q for our beam specifically, we have to times the length, which is 6 meters. So in the end, we get 1.5 kilonewtons per meter. And we repeat this step and the G step for beam B2 as well. Now, we calculate the wind load. Our shed is assigned on the wind region B and wind terrain category TC1. The topographic class is T3 and the site is partially shielded. So looking at the wind classification table, our wind class is N5. Therefore, the ultimate wind speed is 74 meters per second. Now we can use the 74 meters per second to calculate the ultimate limit state, which is 3.28 kilonewtons per meter square. Then we take a look at the pressure coefficients table for wind class, which is minus 1.0 and plus 0.63. So with that information, we can find the inward and outward wind pressure, and we can calculate the combination load using the pressure. We can calculate the combination load. Then we decide to use number 4 and number 5 because they're the largest. Number 4 is for when the top is under compression, and number 5 is outwards when the bottom is under compression. So we can calculate the bending moment of top and bottom compression using the formula M equals WL squared over 8. And we assume that we used a universal beam 410 UB 59.7. We check the bending moment, the shear, and the deflection with our calculations in the next slides. This one is the formula. It's the same for the bending moment when top is under compression and bottom is under compression. However, in this slide, this is just when the bottom is under compression. And in this slide, we calculate for the shear force and the maximum deflection. So now we compare all the values to the beam and our calculation, and we can know that our beam that we selected is safe. The next step is to design for the column. For column, we also need to calculate dead and live load. For dead load, here we add together the flooring G, self weight of rafter, and the self weight of column to get the G for this column. For the live load, we use the table in AS1170 to know the weight of the live load for our purpose of the building. Then we times the load area contributing to the column. For columns, unlike beams, we don't use bending moment, shear, and deflection to see if it's safe. We use axial forces, also known as end design maximum. Then we use the L buckling in plan to check if the column is safe. In the end, we decided to choose 200 UC 46.2 for our column, and it is safe. Then the assignment requires us to use structural designing software, SpaceGas, to design our shed. So we learned how to use coordinates to create a shed, and we change the connection type, input the beams and column, and then input loads, and then in the end we run a linear static analysis. So in this slide here, this is the load case for our shed. And in this slide, this is the linear analysis of our shed in the software. So there's this bending moment, shear force, deflection, and the axial force analysis. Final step is to design a purlin. So we were given the dimensions. So the purlin span is 6 meters, span of the shed is 7 meters, height is 8 meters, and the total length is 12 meters. Roof slope angle is 5 degrees. So we assume the weight of insulation is 0.5 kilograms per meter square. We use suspended ceiling and air conditioning ducts will be used. We calculate the internal spans and external spans, and in the end we calculated that the internal span is 1.56 meters and the external span is 1.17 in between the purlins. Next, we calculate the dead load. The dead load is also almost the same as the dead load we calculated for beam, which is G roof sheets plus G purlins plus G ceilings plus G insulation and plus G services. And in the end, we got 0.76 kilonewton per meters for our dead load. For live load, the formula is 1.8 divided by area plus 0.12 times the load width, and in the end we got 0.48 kilonewton per meter. Now that we have calculated the load, the dead load and the live load, we have to choose one of the roof purlin design and check whether it is safe to use. To do that, we calculate the load combination to get the inwards and upwards load. Then on the capacity table for that purlin design, which is purlin Z/C 20024 double lap span, we have to compare the inward loading and the outward loading to see whether it can sustain the load. In this case, it is safe. There is another step to make sure that the purlin is safe. We have to check the deflection is okay. The load for maximum deflection is on the capacity table. It is the span divided by 150. On AAS 1070, there is the span divided by 300. So from the capacity table, we have to divide by 2 again to get span over 300. So in this case, we compare the deflection we got, which is 6.81, and our loads, which is 0.759. This means that our purlin is safe and it will not deflect. In conclusion, there are 4 main things that we learned during this assignment. That is how to design for beam, how to design for column, and how to use the program SpaceGas, and also how to design for purlin. Thank you very much.